In this video, we see how to work with defective eigenvalues. We'll come right out the gate with our definition. Consider a matrix A and suppose that its eigenvalue of multiplicity R has some defect. Then we'll make up for the defect by defining a chain of generalized eigenvectors, starting with an actual eigenvector v1. This satisfies a minus lambda I v1 equals 0. Now we define a new vector v2 as satisfying the eigenvector-like condition a minus lambda I v2 equals v1. And we have the additional restriction that v sub 2 is not an eigenvector. We define v3 as a minus lambda I v3 equals v2. And again, v3 has the additional restriction that it does not satisfy either of the eigenvector condition or the first generalized eigenvector condition. Remember the setting we're working in. We have some eigenvalue of some multiplicity. For example, multiplicity 7. But we have fewer eigenvectors than this. Say we have 4. We're getting 4 solutions out of the 7 we need. we've selected one of these eigenvectors and started creating generalized eigenvectors. Each of these is giving us a solution so if we can get 3 of them plus the additional eigenvector, we're golden. 1, 2, 3, 4, 5, 6, 7 solutions. Or maybe we can't. Once we reach a certain point, we may not be able to find any further generalized eigenvectors. Maybe every vector that satisfies this condition also satisfies one of these equalities that we're not allowed to satisfy. So our chain stops there. Well, in that case, we simply move on to the next eigenvector and start again. Eventually, we will get as many generalized eigenvectors as we need. So suppose we have a chain of generalized eigenvectors starting with a real eigenvector. These give solutions as follows. The eigenvector gives the solution you're used to. The second eigenvector, the second generalized eigenvector, gives us the solution we saw in the 2 by 2 case. The third gives this polynomial as its solution. And the general formula is this unappealing looking thing. Note that as the V's go up, the powers go down. In this video, we have seen how to deal with eigenvalues that do not give sufficiently many eigenvectors. In doing so, we have considered all the cases and can theoretically solve any system of linear homogeneous differential equations. Although outside the classroom, we'll need to use some software package to find the eigenvalues and eigenvectors we need.